Hi guys, so we have seen what Laplace transforms are, we saw how they work and how they can be useful in engineering systems. Let's now actually apply them to solving linear differential equations. So here we have a 1 degree of freedom mass damper system. Okay, the mass is equal to 1, m. We have a force applied to that mass equivalent to exponential of minus 4t, t being the time variable as usual. We have x, the displacement, and the derivative of x, the velocity, v. And we have a damper, which is between a mass and a fixed point, let's say on the ground or on a wall. And the damping coefficient of that damper is c equal 7. The initial condition of this system is that at t equals 0, so when everything starts, the mass is actually moving at a velocity of 2. So in the same direction as the arrow next to x, it's moving in the positive direction at a velocity of 2. Using the mathematical equations we have seen in previous lectures, it is very easy to construct a model for this system. We can simply write that the mass m multiplied to the acceleration of the mass, which is the second derivative of x with respect to time, plus the damping coefficient c multiplied by the derivative of x with respect to time is equal to the force F. Okay, so you have the second law of Newton on the first term, the equation for the damper on the second term, and then the force, which is equal to these two. So actually rewriting this in actual terms, we get that the derivative of the velocity of the mass with respect to time plus the damping coefficient 7 multiplied by the derivative of the displacement, which is the velocity with respect to time, is equal to the force exponential minus 4t. You can note that because m equals 1, it simply disappears. So using the table I gave you before, we're now going to take the Laplace transform of both sides. First of all, we can apply the linearity property to the left side of this equation. So instead of doing the Laplace transform of the whole left side, we can first do the Laplace transform of the derivative of the velocity of the mass with respect to time, to then do the Laplace transform of the velocity of the mass with respect to time. We can then multiply by 7 that Laplace transform and do the sum of the two Laplace transform we just calculated. The right side just remains the same. Okay, so we're going to use the following Laplace transforms from the table that you can see in the previous lecture. So the Laplace transform of the velocity with respect to time is v of s. Okay, the Laplace transform of the derivative of that velocity is equal to s multiplied by v of s minus the initial condition, the velocity at t equals 0. Finally, we're going to use as well the Laplace transform of exponential minus a t, which is equal to 1 over s plus a. We actually saw this before. So applying these Laplace transforms, we can rewrite the equation as s vs minus the velocity at the initial condition of t equals 0 plus 7 times vs is equal to 1 over s plus 4. So we solve for v of s. Okay, we solve for the velocity and we actually use v0 equals 2. That's the given that we have to solve that equation. So we get that s plus 7 multiplied by v of s, by factorizing we get this value on the left, is equal to 1 over s plus 4 plus 2. So this is actually the initial condition that we have moved to the other side. Eventually, we can write that the Laplace transform of the velocity with respect to time of the mass, so v of s, is equal to 1 over s plus 4 multiplied by s plus 7 plus 2 over s plus 7. Okay guys, we can factorize that further by writing that v of s is actually equal to 2s plus 9 divided by, in parenthesis, s plus 4, closing the parenthesis, multiplied by s plus 7. Okay, so this looks a lot nicer than the differential equations we had before. I'm sure we all agree about this. Now all we have is an algebraic expression with s the only variable. So we need to convert this relationship into standard transforms, which we can then invert using the table of Laplace transform pairs to find the value of the displacement xt. What we want is for the equation to look like something we can recognize in the Laplace transform table, and then apply one of these equations in the Laplace transform table to move back from the Laplace domain to the time domain, so where s essentially disappears and we get t instead. As a little tip, we know already that we use the Laplace transform of exponential minus a t equals 1 over s plus a to get there. So probably we're going to have to use that one, but in the opposite direction to get to where we want. Also, you can look at the denominator and see that the two factors are s plus 4 and s plus 7. So it already kind of looks like what you want it to look. The difference is that you need it to be a sum. Okay, so this is where partial fractions come into play. It's a little mathematics trick that is very useful in this case. So simply we have our equation, okay? Vs equals 2s plus 9 divided by s plus 4 multiplied by s plus 7. We can rewrite this by creating two variables, a and b. We don't know what they are. We're just going to write the equation. So the equation the way we want it. So we have a over s plus 4 plus b over s plus 7. Now we can develop this equation to look back like the first one, so we can clearly identify which terms are equal to which terms. So developing this, we get that a plus b multiplied by s plus 4b plus 7a divided by s plus 4 multiplied by s plus 7 is equal to the equation from the beginning. So what you see is that in the numerator, in the number above, you have a number multiplied by s in both sides. Okay, so on the left it's 2, on the right it's at a plus b. So you know that a plus b is going to be equal to 2. Okay, you can do the same with the number that is not multiplied by s. So you have 4b plus 7a is equal to 9. Simply you can now develop this, put the equations back together, and you get that b is equal to 5/3 while a is equal to 1/3. We can now replace this in the equation that defines Vs. So we get that Vs equals 2s plus 9 over s plus 4 multiplied by s plus 7, but it also equals 1 over 3 times s plus 4 plus 5 over 3 times s plus 7. So, like I just told you, we can use the Laplace transform table again since we have terms of the form 1 over s plus something, okay? And then reversing that, we can go back to exponential minus somethings times t, okay? So replace the something by the number that is in the equation, okay? The something is just a constant. So we just take the Laplace transform and reverse it. We can apply that to the equation for Vs. You can use linearity properties to make it even easier. So you can put the 1/3 out, put the 5/3 out, as well as apply the Laplace transform one by one on each term of the sum. So once on 1 over s plus 4 and then once on 1 over s plus 7. And what you get is that v with respect to time, so the velocity of the mass, equals 1/3 of exponential minus 40 plus 5/3 of exponential minus 70. So here exponential minus 40 is the reverse Laplace transform of 1 over s plus 4, and exponential minus 70 is the reverse Laplace transform of 1 over s plus 7. What does this equation mean exactly? So when we established the example, when we gave the problem, we saw that the force applied to the mass is actually equal to exponential minus 4t, t being time as usual. So we can actually plot this as a force with respect to time. So if we give an initial step input of 1 as the force will exponentially decrease to 0 and reach a value of 0 between 1 and 1.5 seconds. Okay? So the equation we have actually gives us the response of the system to that force. Okay? So you can see that the plot on the right will be the velocity of the mass with respect to time after the force of 1 has been applied suddenly to the system. So we just created an equation that tells you exactly how the system is going to react to that force exponential minus 4t, and then allows you to find out what is the velocity of the mass. You can also integrate that velocity and find its exact position at different times. Okay, so I know it's a bit complicated, but it's also very exciting to know that through mathematics we can find such things that happen in the real world. It looks kind of daunting at first, but I promise you that once you start practicing Laplace transforms and mathematics models of engineering systems, it gets much more easier over time. At some point, it's something that you can do super fast and super easy. It's just about finding the right equations and knowing when to apply them. So I hope everything was clear enough. If you have any questions, please do not hesitate to ask me. I will be very happy to help you. Thank you, guys.